What's up guys, Major Math with another video on fluid mechanics. If you have any questions, drop it in the comments, and if you're having trouble with other problems, I've attached my email in the description, so please feel free to reach out. Without further ado, let's get started. Question 3.135 says determine the minimum volume of concrete with a specific weight of 23.6 kilonewtons per meter cubed needed to keep the gate that is 1 meter wide in a closed position with L equaling 2 meters. Note the hinge at the bottom of the gate. Okay, first step, write our goal. What is our goal? Determine the minimum volume of concrete needed to keep the gate closed. So we need to find volume that keeps the volume of concrete. The minimum value that keeps the gate closed, okay? And then our givens, specific weight of concrete equals 23.6. I'm going to go ahead and convert that to newtons. So times that by 1,000. 23,600 newtons per meter cubed. The width is 1 meter. So the width is what is going into the page, kind of like this way. That'll be useful when we're finding the area of the gate. And then it says L equals 2 meters. So probably can't really see this. This is an L right here. So that's 2 meters, and that says 1/4 L. So this area between the water and the cable or rope for the pulley system is 1/4 L, so that would be 0.5 meters. Okay, assumptions. To make this work, if you've ever taken physics, we're going to have to say that pulley is frictionless and weightless, as well as the cable or rope, whatever it is also weightless. And then it says, does it not say? I think in the textbook it says that the temperature is 10 degrees. Nope, you gotta assume it. Okay, we're gonna assume that the temperature is 10 degrees Celsius. So that means that the specific weight of the water is 9,810 newtons per meter cubed. Alright. So the first step we're going to want to do is a little free body diagram. Let's make some notes on this diagram real quick. Just thinking about some of the forces in play here. So we got, I wrote it the wrong way. We got tension in this rope, right, going away. And this whole thing's the gate, by the way. This whole line is gate, and it's hinged right here. So this, the only thing keeping this gate closed is this concrete, right? So we got tension going away from the gate. We got tension going away, tension in that cable away from the rope. And then we got the weight of the concrete. And then we also have the buoyancy force. So the wanting of this concrete to float or buoyant or bounce up instead of being underwater. Okay, so thinking of some of these forces, and since the pulley is weightless and frictionless, these tension here and tension here will be equal to each other. So that's important to keep in mind for later. So step one, let's draw an FBD of concrete block. So this is all underwater. we're going to have this rope, and we got tension, and then we also got the force of buoyancy, and then we got weight, which is weight of the concrete block, which we know is mass times gravity. We only have forces in the y direction, so we got tension going up, we got buoyancy force going up, and then we got weight going down, which equals 0. Let's rewrite this. We got tension equals weight minus buoyancy. Another way we can rewrite mass times gravity is the specific weight of concrete times the volume of the concrete, and then the formula of force of buoyancy. Buoyancy force is specific weight times that'll be the specific weight of the water, because that's what the water is, the force trying to bring it up, and that's what it's in, times the volume displaced, which in this case the whole concrete block is underwater, so it's just going to be the volume of the concrete. Okay, and then we can plug in what we know. So we know specific weight of concrete, we know the specific weight of the water, and then we don't know the volume and we don't know the tension, but we need this relationship for later because we're trying to solve for this volume, right? But we need, so then we're going to need to solve for this tension, and then once we solve for tension we can use this formula. So then we get tension equals, if I were to okay, so these volumes are the same because all of it's displaced underwater in the volume of the concrete block. So I brought the volume out, and leaves me with the two specific weights inside, filled in the numbers, and then so we'll be left with, if we want to solve it for volume, left with 13,790 newtons per meter cubed. No, I wrote, that should be on the bottom. We'll have tension over 13,700. Okay, so we have a good relationship here between volume and tension. So now all we gotta do is figure out how to find tension. So our next step is to draw a free body diagram of the gate to try and figure out this tension. Okay, so our gate, it's nice that it's not slanted or anything, so we don't have to do any extra steps. It is completely upright at 90 degrees. So we got tension from the rope coming here, right? This is the gate. The water is somewhere down here, and then this is that rope pulling it. I remember from what this looks like. So I'm drawing this gate right now on the right. So we got our water, and then this is where our pressure starts coming in. So I'm drawing that triangle for an upright panel. So we got pressure. The deeper we go down, the more pressure acts. We know that this is 1/2 meter, and then this is 2 meters. That's the part that's underwater. We know the centroid of this is at 1 meter because it's a rectangular gate, so the centroid is just half. And then we also know, since it's completely upright, we know that the center of pressure, where we are going to say that the force of pressure acts, is 2/3 down, because it's that upright. So we know that it will act 1.33 meters, right? Because 2/3 of 2 is 1.33 meters. That's how I did that. So that's where this lines up with the center of pressure. And then we know that the pressure force acts at the center of pressure. We have our tension, and then we have our hinge right here, right? So now we have this FBD. If we take a moment about the hinge, we can calculate the tension, right? Because we can calculate the force of pressure, and then if we take a moment about the hinge, we know that force of pressure, we can actually solve for tension. So real quick, we need to solve for that force of pressure. So that will equal the S, which equals times so we know that it is the height where the centroid is 1.5 meters. Nope, it's just 1 meter because it's to the surface of to the water, not to the okay. And then the area, it's a rectangle. It is 2 meters tall, and it said it has a width of 1 meter. So the area is just 1 meter width times the 2 meter depth, so 2 meters squared, and that gives us a value of 19,620 newtons. Okay, so now we can take this moment. So let's take a moment about this hinge. Let's see. Counterclockwise is positive. That equals 0. So take the moment. We need the pressure force times perpendicular distance to find that moment, and this will be negative because if you take this force and push the hinge, it'll be going clockwise, and then tension pulling it will be going counterclockwise. So, and this will be tension times the perpendicular distance, which in this case is half a meter plus the 2 meters, so 2.5 meters. I'm gonna go ahead and fill this in too. I don't know why I didn't do that earlier. This is from here to here, so let's see, 1.33, so we got 0.77, 0.67, yep, 0.67 meters. So all I was doing is trying to find the distance from here to here to find that perpendicular distance of the pressure force. So I just did 2 minus 1.33. That says 0.67 meters minus tension times 2.5 meters, and that all equals 0. So I gotta fill this in. I'm gonna go ahead and fill this in as well. That the pressure force 9620 newtons. And then now we can solve for tension. So 2.5 meters times tension equals let's do this. Tension equals 9620 newtons over 2/3. 2/3 is equivalent to 0.67 meters. It's actually more accurate. And then you have that 2.5 meters on the bottom, and then you get that tension equals 5,232 newtons, and that is positive, so I put it in the right direction. I assume the right direction for that is going left, which we should have known because it's tension. So I found tension. So now that I found tension, I can plug it into this original equation that I found to find the volume of the concrete. So let's go ahead and plug that in. And then this volume of the concrete equals, this is the tension, I'm just filling it in, and this is the differences in specific weight here. And if you divide that, you get a volume of 0.379 meters cubed. So this will be the minimum volume required for the concrete block to make sure that the gate will stay shut. Thanks for watching, soldiers. Don't forget to leave a like and subscribe for more content like this. If you have any questions, leave it in the comments, and if you need help with any other problems, feel free to contact me with the email shown on the screen.